Hi everyone, my name is Lior, I'm the head of Starknet core engineering at Starkware.
I'm Gidi, head of core engineering at Starkware. This is the official announcement. It's been open since this morning, and I'm sure all of you have already cloned the repo.
Yeah, so today we're going to talk about Stone, the now open source prover. As Kinet mentioned earlier, Stone is the prover that we use in production. Okay, so we're going to talk a few important concepts, then see a demo. Then we're going to talk about the stages of the prover, talk about some configurations, some way to affect both the prover and the proof, and then see some code, and if we have time, we'll have a short Q&A. Okay, so these are the concepts that I want to talk about briefly before we see the demo. The first concept is, of course, STRK. The STRK is a protocol. It allows one party, let's say Alice, to prove to another party, say Bob, that a certain claim is true, that a certain computation was run successfully with some output. For example, Alice may want to prove to Bob that the 10th Fibonacci number is 144. And she can do this using the STRK protocol. Alice uses a tool called a prover to create a file, a proof file, and sends this proof to Bob. Bob uses a verifier to check the validity of this file, and if the file is valid, if the verifier says that the file is valid, Bob is convinced that the claim is true. Okay, next concept is called AIR. AIR stands for Algebraic Intermediate Representation, and this is the way we describe what is the computation we want to prove when we use the STRK protocol. And AIR is basically a table of numbers with some polynomial constraints on them. You can see in this slide an example of an AIR for the Fibonacci case. And the constraint here is that the sum of every two consecutive cells is the value of the next cell. Now, while this AIR is relatively simple, usually AIRs are much more complicated, and it is very difficult to design an AIR for an actual computation that you want to prove. Again, maybe for the Fibonacci case it's simple, but in general it's not. And it's also, in addition to the fact that it's not easy to design, and it's also not easy to maintain them and to audit them. Ideally, we would want to be able to describe the computation we want to prove using code instead of a list of polynomial equations. And this is why we have Cairo. So the next two concepts are CASM and the Cairo AIR. CASM stands for Cairo Assembly, and this is an instruction set like x86 or EVM, but unlike x86 and EVM, Cairo was designed to be efficient for proof generation. The next concept is the Cairo AIR. This is a specific AIR, a single AIR, that executes CASM code. And if you take this Cairo AIR with the STRK protocol, you get a program that can prove any CASM program without changing the AIR. And this is what you have in the Stone prover repository. You have an executable that does this. Okay, last concept before we see the demo is called built-ins. If you look, when we move from a designated AIR to using Cairo and the Cairo AIR, we get expressibility, but we lose performance. And built-ins is a way to mitigate this issue. Built-ins are part of the Cairo AIR that are designed to do specific tasks, like hash functions. And if you use the built-ins, then you have negligible overhead for these specific tasks. The Stone Prover comes with the following built-ins. We have built-ins for hash functions. We have Peterson, Poseidon, and Ketchuk. We have built-ins for elliptic curve operations and signatures. Specifically, we have ECOP and ACDSA. And some utility built-ins like range checks for comparisons and bitwise for bitwise operations. Okay, it's time to see a demo. I have here a clone of the Stone Prover repository. Let me open the README file. I hope you can see. Okay, the first thing I'm going to do is to build the two executables, the prover and the verifier. And I will do this by building the Docker file that exists in the repository. Now it should be cached. Okay, yeah, so this was quick. It may take more when you run it the first time. Now what I can do is to extract the two executables from the Docker, so I'll do that. And now I have two executables, CPU prover and CPU verifier. You can also, if you don't have Linux, you can also go inside the Docker and do this demo from there. Okay, the next thing I need to install is the Carolang package. This will allow me to compile the Caro code that I have and get the chasm that I need in order to generate the proof. Okay. So let's go into the E2E test folder here. We have 4 files. The most important one is called Fibonacci.caro. One second, I don't need them. Okay, what I have here is a Cairo 0 program that computes the nth Fibonacci number. I'm going with the claim that the 10th Fibonacci number is 144 for this demo. What this program basically does is that it takes the index from the program input and then outputs 2 things. It outputs the index of the Fibonacci number that we computed plus the value of the Fibonacci number. Okay. Now I need to compile this program. So I use the Cairo compile command from the Carolang repository. Let me do this. And I get a new file, Fibonacci compile.json. Great. The next thing I need to do is to use Cairo run to run this program and then get something that I can use with the Stone Prover to generate a proof. There is one file here that I'm using as an input. It's called the Fibonacci input. It's a very simple file. It just says that I want to compute the 10th Fibonacci number. Okay. So let me run this. Okay. You can see here the program output, which is 10, which is the value, the index that we wanted, and 144. This is the result of the computation. And I have here now a few more files that were created, and I'm going to run the prover now. Okay. Okay, great. I should have now a Fibonacci proof file somewhere. Yes. Okay. Next thing to do, let's verify this proof by running the CPU verify executable. And we got that the proof was verified successfully, which is yeah, which is what we wanted. Now let me show you the proof file itself, and let's do some changes and play with it. So this is the Fibonacci proof.json file. This is a JSON file. It has some sections. I will go over them. First, note that there are some sections here that are not necessary for the verification. For example, the private input here is just for completeness. You don't need the private input to verify the proof. So I can just remove this. Okay, proof parameters is actually important. Prover config, also I don't need it. Basically, there are two configuration files in the directory that I needed to, in order to run the prover. One controls the proof itself. It's called proof parameters. And the second one controls the prover optimizations. For example, you can turn on and off some of memory optimizations. Gidi will talk more about it later. Okay, so prover config, obviously I don't need this section to verify the proof, so I can also remove this one. We can run the verifier again. Yeah, okay, we got the proof is still valid. Probably the most important field in this JSON is called proof hex, and this is actually the bits of the proof. Now let's try and change. I have 4 here. Let's replace it with 5 and try to verify again. Okay, so we got that this is an invalid proof. I shouldn't do this, so let's go back to 4. Okay, proof parameters. I'll skip this. Gidi will explain more about this section later. And the next section I want to mention is called public input. If you noticed, when we ran the verifier, we didn't give the verifier the Fibonacci program, not before and not after the compilation. And we didn't give it the numbers 10 and 144. So you may ask yourself, what exactly are we proving here? It just got the proof and says the proof is valid. So the answer is that the CPU verifier executable just checks the consistency between the proof and the public input section. The public input section contains all the information that we need to know about the program and the program output. So let's see that. We have some memory segments here. I will start with the program segment. And the program segment, you can see, begins in address 1. So let's go below. We have a section called public memory, address 1. And I see this weird value. And let me show you where this value comes from. So I will open the Fibonacci compiled JSON. This is the result of the compilation. And this is actually the CASM as bytecode. And this is this number. The first number here is this one. And if you look, let me close this. If you look and compare the two, you can see that what we have on the right-hand side is exactly the numbers that we have on the left-hand side. This is the program. If you want to know that this proof actually proves the Fibonacci code, you need to check that these values are correct, are consistent with the compiled program. Okay, another important section is called the output segment. and you can see that it starts at address 95 up to 97, which are now addresses 95 and 96. Let me go below. So addresses 95 and 96, I can see the values 0xa and 0x90. 0xa is 10, 0x90 is 144, and these are the outputs of the program. Now, I can also try to change this. Let's change the 0x90 to 0x91 and save and see that now the proof fails again. Okay. Yeah, so we cannot use this proof to prove that the 10th Fibonacci number is 145. It's not true. Okay. The last thing I want to show you, for this I will regenerate the proof, this time with a flag called generate annotations. Okay. And generate annotations creates another section in the proof file called annotations. And to understand this section describes what's going on inside the proof. And to understand this section, you should know that the STARK protocol is built from an interactive protocol that was turned into a non-interactive version using the Fiat-Shamir heuristic. And this section describes the simulated interaction between the prover and the verifier. So you can see, for example, that the proof starts by where the prover is sending to the verifier some value, and then the verifier responds with some field elements, and the prover sends another value, and so on. For every value that the prover is sending to the verifier, you have these numbers here, which says which bytes in the proof correspond to this line. So you can actually, this starts with 0x92c, so we should find it in the proof X, I hope. Yeah, so the proof X, this is exactly how it starts, and you can use this if you want to understand what's going on inside the proof. Of course, this section is not needed for the verification. It's just for debugging. Okay. Giddy.
Okay, just to mention, the verifier also has a flag to generate annotations, and then you can compare the annotations of the verifier with the annotations of the prover, especially when debugging provers and verifiers. That's very useful. So let's talk a little bit about how this prover performs this Stark proving. As you know, there are many algorithms for Stark proving, and we'll talk about the specific algorithm implemented in this prover. The first step is basically generating the trace. Generating the trace is turning the execution of the Cairo program in a series of numbers or field elements. The prover looks at these field elements as representing polynomials. So you can think of a big table of numbers, and each column in this table represents a polynomial, relatively large polynomial. Trace generation is statement specific. When we say statement, we talk about what the prover is proving. So in our case, we're talking about proving statements of the Cairo error. Other statements are also possible. So if you want to design your own statement and hook it into the same code, then you can do that. And in order to generate the trace, you will need to implement a logic that generates the trace for your specific application statement. In case of Cairo, this includes the execution trace, and it includes the memory as it appears in the output of the program, or in the running of the program. After we have the trace, the next step is what we call a step of low degree extension. So if we looked at the trace as a table or as columns or as polynomials, we can perform an interpolation of these polynomials to a larger space. This is what we call the low degree extension. It uses what is normally called in the industry the NTT algorithm. In our code, we call it FFT because basically it's the same thing. So those of you who will take a look at the source code will notice FFT. There's no mention of NTT there. This is a parallelized implementation in the Stone prover. The parallelization is both within a single FFT as well as running multiple FFTs in parallel. So the more CPU cores you throw at this prover, the faster it'll compute the NTT. And finally, we commit on this low degree extension. So we take this extended trace, which is basically a multiplication of the size of the original trace by 2, by 4, by 16, and we commit to that. We use Merkle commitments for that, and in fact, we have the ability to use multiple hash functions within the same Merkle commitment. We use this in order to optimize performance for cases where you submit the proof to a Cairo verifier. Cairo verifier was mentioned here, I think, in multiple talks. It's an implementation of the verifier. The verifier is these proofs, but in Cairo instead of in Solidity or in C++, as was demonstrated before. For Solidity, catcheck is a very useful hash function to use Merkle commitments for and decommitments, and is also very CPU friendly. For Cairo verifiers, we typically use other hash functions like Peterson and Poseidon or Blake. This is configurable within the prover. The third step is an extension to the trace. We use this step basically to generate additional columns to the original trace. But we don't do this simultaneously in the beginning because we want to achieve here something that is difficult to express in standard constraints. For example, we want certain constraints on tables of values, in particular of memory values. We want to say something like in a certain address in the memory, there's reference to a value, and that value is only one value. So we don't want to make we want to represent a read-only memory or a lookup table, if you like. And if the program references that address multiple times, we expect to see the same value in the same location. The way we verify this is by generating additional trace columns, which represent an ordered series of values in this memory, and then using some interaction, that's why we call it the interaction trace, we can validate that the interaction trace corresponds to the original trace in a way that attests to the fact that the value is consistent to the constraints that we want. On this additional interaction trace, we do the same functions of low degree extension and commitments using the same mechanisms. Fourth step, and we're nearing the end. We need to apply the constraints to the trace. The trace in itself, you can think of it as a series of numbers representing an execution. Now we need to apply constraints in order to validate that this execution is according to the rules of the air, of the CPU, the virtual machine of Cairo. That's what the constraints are about. And basically, we build the constraints on top of the original trace. Both the constraints are polynomial, and the trace is perceived as a polynomial, so the result is a composition of two polynomials, and that's why we call it the composition polynomial. The degree of the composition polynomial is basically the degree of the trace and multiplied by the degree of the constraints. So the higher the degree of the constraints, the larger the composition polynomial, of course. We commit to this polynomial, and then we use out-of-domain sampling, or LEAP, in order to create a virtual oracle for the final step of the STRK prover, which is the low-degree test. We use Fry for low-degree testing, and the low-degreeness is tested on this virtual oracle. This is the only polynomial that we apply the test to, but in turn, it implies the low-degreeness of all the preceding polynomials. Which means that we basically prove the low degreeness of everything from the beginning, including the trace, of course. Fry includes a query phase. If you're familiar with Fry, it's basically a certain series of commitments on ever-shrinking polynomials until we reach a very small polynomial that we can just send to the verifier. And then we perform queries that validate the consistency between all these polynomials all the way back to the trace. The more queries we send by the verifier, the sounder the proof. So we need to repeat this multiple times. But for every query, we get results, decommitments of the original commitments, and these are included in the proof. So the proof increases in size. So the prover includes an additional option, which is the ability to reduce the number of queries, but still make the prover spend more time in generating the proof by using a proof of work mechanism, so we can slow it down for every action performed. The result is that we can improve soundness without increasing the number of queries. So you can actually tweak the prover to do more proof of work and require fewer queries, which means a smaller proof, or you can do less proof of work and do more queries, something that you can trade off between the two. Let's look a little bit about how we can configure the prover. So as Leo mentioned before, there are two aspects to the prover configuration. One aspect is relevant to both prover and verifier, is a definition of exactly how we use the Stark prover. So things like the number of queries, the degree of extension, we call the blow-up factor of the trace, is something that we need to agree upon between prover and verifier. We call something called Fry steps. Is in the Fry algorithm itself, we can skip layers. These are the steps. The steps need to be consistent with the size of the trace. This is a parameter that is also a configuration of the proof. And some of these together basically imply the soundness of the proof. In code, it looks like this. It's basically a JSON file with parameters inside. The top parameter here specifies the field on which the prover works. The prover supports multiple fields, but when you want to run it with Cairo, you need to use the field that is used by Cairo in Starknet. Here it's called prime field 0, which is the Starknet prime field, 252-bit field. But if you want to prove something else, you could run this prover on a different field that you need to define, and you can use a couple of fields are included in the code base, but you can also define your own. Then there comes a section which we call Stark, which is the parameters of the proof themselves. So I mentioned a couple of them. One is the number of queries, as mentioned here. The more queries there are, the higher the soundness. Every query contributes a few bits to the soundness depending on the blow-up factor. So the blow-up factor here is defined by the bottom parameter pointed here, log n cosets, which basically means the number of, or basically the size of the trace that we blow up. Or basically in the low degree extension, we multiplied the trace size by a certain number. So log n cosets of 4 means we multiplied by 16, okay? And this, at the same time, means that every query we consider as 4 bits of security. If you want to be very strict about it, this is not a proven bound. You can reduce that by 50%, which would imply 2 bits of security. Finally, as I mentioned, we can trade off queries for proof of work. So in this case, we told the prover it should do 24 bits proof of work, which implies we need fewer queries. So if you take the numbers in this example, the soundness of the proof that is expected would be 4 times 18 plus 24, and that's the soundness that you get. So in this case,
I think
quick calculation should be 96, I think. And if you want to be stricter about it, fewer bits. The verifier should be configured, of course, to accept these proofs. So if you set the verifier to accept only proofs that have a certain soundness or above, then it will reject proofs that are sent with lower soundness. Other aspects of the prover have nothing to do with the verifier, have to do with a program that has certain parameters, can run at certain speeds, can consume certain amounts of memory, and it really depends on the compute platform that you run it on. One of the interesting tricks that we use in this prover, as I mentioned, and of course this is included in the open source, as anything else, this is the production prover that we run today. It includes an optimization that allows us to run even if, for instance, the low degree extension of the trace is larger than the memory of the system that is actually running the proof. So how is this possible? As I mentioned in the various steps of the proof, we perform low degree extension and then we need to commit on that. But if you think about that, in fact, we can commit in stages, and every time we perform a commitment, we can actually forget about the data underlying that commitment and just keep the hash that represents that. So as we move forward, we can continue to perform calculations and just keep a minimal amount of memory that is needed in order to remember those commitments. So if you think about Merkle trees, you can think about kind of calculating subtrees, remembering their hash, calculating additional subtrees, remembering their hash, and then combining them together to the root of the total Merkle tree. In low degree extension, we can do something similar. We can begin with a polynomial, apply it to a certain subspace, get a new coset out of the original trace, commit on that, erase it from memory, and repeat again. As a result, and similar optimization also is applied to the Frye algorithm. The result of this is that you can actually generate quite significant proofs in servers that don't have that much memory. If you're doing it on very large proofs, it is very important that it reduces the footprint of the server. If you want to do small proofs, it is also very useful to fit into very small compute platforms. So it's useful also for if you like to run on phones or laptops and you want to have the ability to run slightly slower but with much less memory, these optimizations are useful. Out of the box, the prover will utilize all the cores available on the system. It uses a system call to understand how many cores are available, but you can also limit the usage of the cores that the prover consumes. It's a command line parameter. By the way, you can just type -- help, and the executable will tell you what the parameters are that you can use. And finally, we have the ability to control annotations, as demonstrated by Leo, as well as have some performance analytics. If you're interested in the runtime of the various stages of the prover, there is a command line flag that allows you to perform that, and accordingly, you can do some analytics that show you exactly each section and the runtime corresponding to that. Similarly, this is controlled by a JSON file. I'm not sure we want to go through every one of these parameters, but for example, here we're talking about configuration of the low degree extension. The top parameter that is mentioned here, store full LD, stands for do we keep the result of the low degree extension in memory or not? In this case, we don't. When we don't keep the data, where does the data come on when we reach the query phase? Nobody asked, because I didn't ask you. So where does the data come once we need to answer those queries? Any ideas? We threw it out of memory, so we need to recreate that data. Recreating the data in a naive way would be to perform the beginning again. So we have now a specific query in mind, and we need to answer what the data was somewhere in the low degree extension. We may need to recalculate the NTT. But since there are a limited number of queries, maybe it's more efficient not to run an NTT which actually creates the entire low degree extension, but just to recreate certain points in the low degree extension which can be calculated possibly more efficiently by point-wise calculation of the interpolation. And that is what we do using the flag use FFT for evaluation. False means we actually calculate it point-wise. Similarly, we also recreate Merkle based on the recreation of the low degree extension. Merkle memory out of memory Merkle layers is the number of layers on the bottom of the tree that we throw out of memory before moving on. Every layer that we throw out of the Merkle tree reduces the Merkle memory footprint by exactly 50%, since it's a binary tree. And the more layers you throw out, the smaller your memory. At a certain point, it doesn't really make sense to throw it out because it's very little memory. Okay. Numbers. I know you're all excited to hear about the performance of Stone. So I ran it on a few very small examples on my laptop. A 4-core Ubuntu laptop inside a Docker. Of course, this doesn't represent anything. Do your own research. run it on the selected hardware that you want to run your proofs on. If it's a very large server or a very small platform, it doesn't matter, but do your own benchmarking. It really depends on the size of the proof, depends on the configuration of the prover. Do your own experimentation. I'll present a few graphs of the numbers underneath this graphic, representing how out-of-memory responds, how the number of queries, how low-degree extension works. But as I mentioned in the beginning, these numbers are basically very, very dependent on the way you configure and the platform you run on. So there are numbers underneath, and I'll show them in graphs. I think this is a little bit more convincing. So in this case, we have multiple runs of the same prover for a Fibonacci series instead of the 10th element, the 1000th element. Okay, so it takes a little bit more time. In this case, it's under a minute, but as you can see, with different configurations, different runtimes, which are the dark bars. On the left-hand side, you see different memory consumptions, which are the light bars. The left axis is megabytes, and the right axis is seconds. Okay, so I hope these graphs make sense to you. On the left-hand side, we have a prover configured with aggressive out-of-memory, or somewhat aggressive out-of-memory. 6 layers of the Merkle are thrown out. So typically, Merkle will consume 1/64th of the original memory consumed. We use a high low-degree extension of 16, which means that the prover needs to run for a long time to create a large low-degree extension. And that's why this prover ran for roughly 44 seconds, again, with all the disclaimers I mentioned before, and consumed roughly 280 megabytes. So it's not a significant amount of memory, but it's also not a very important statement. Running exactly the same proof when we configure fewer out-of-memory layers just consumes more memory. As you can see, now we threw out only 1 layer of the Merkle, which only saves us 50% of the Merkle space. And the result is that we consume 470 megabytes versus the original 278. Okay, so almost double the memory. Of course, we could have done more aggressive stuff. But this is just to show an example. Runtime is roughly the same. It's basically a variance resulting from me running this on a laptop that was busy with my browser and all kinds of other stuff in the background. Going again from the left, the third example is exactly the same configuration as the second from the left, except that here we do a low-degree extension, which is much smaller. So we only do a blow-up factor of 2, or log n cosets is 1, so 2 to the power of 1 is a by 2 extension of the trace. Immediately you see the runtime dropping by 50% in this case. Memory consumption also goes down a little bit because Merkle consumes less. And finally, on the right-hand side, we have the most performant run of the prover by doing a minimal low-degree extension, factor of 2, and keeping everything in memory. So during the query phase, we don't need to reconstruct any data. It's all kept in memory. So we consume the maximum memory, as you can see here, but at the same time, we get the lowest runtime, in this case, 14 seconds. Okay, so this is a trade-off between runtime, memory consumption, and soundness of your proof, soundness or size of your proof. So if you have a smaller low-degree extension, queries are worth fewer soundness bits. You need more queries, you get a larger proof. Another example here is just running different sizes of statements and seeing how that affects the running of the prover. So in this case, I ran the same statement, but for different indexes of or different lengths of the Fibonacci series. So the trace length of the program was different. On the left-hand side, we had a Fibonacci length of 10, which was the example that Lior ran before. In this case, it resulted in a trace of 8,000 elements. Or at least the Frey polynomial was of size 8K. In the middle, we have a Fibonacci series, which is 10 times that. But since this can still result in a trace that's not exactly 10 times that size, it actually fit in a relatively small trace. And on the right-hand side, we have a Fibonacci series, again, 10 times larger, Fibonacci series of 1,000 elements. And the trace grew, as you can see, by a factor of 8 versus 100. So in fact, the Fibonacci series of 10 is not very efficient because of all kinds of reasons. And as you can see, accordingly, memory size grew. And I think what is most apparent is that as the trace size grows, the proving time grows roughly linearly. Theoretically speaking, it's an n log n prover because that's what NTT takes. But de facto, the logarithmic factor is not very dominant, especially not in small proofs. Okay. It's open source, so feel free to dig through the code, look for hidden features. I mentioned a couple of these. Performance profiling can be done with command line flag -v1, and you can see the output there. I won't demonstrate it here. Generate annotations was demonstrated by Lior, and there's a lot more to understand from the code itself. Which brings us to the code. Leo, you want to begin? Or do you want me to begin?
Yeah, let me just... So, do you want to start?
Yeah, okay.
Okay.
So,
we don't have a lot of time because I want to have some time for questions, so we'll do it
briefly.
Briefly, yeah.
Okay, so let's begin from the STRK itself. Okay, there's a file. The prover is written in C++. I don't know if we mentioned this. And there's also a verifier, and it's also written in C++. And there's a file called stark.cc, as you can see. And proof stark is a function that holds the top level of the proving phases that we mentioned before. So in the top part of this function, you can see the trace generation over here. Next step would be, where is it? Committing to this trace. You can see committed trace, so roughly corresponding to the slides. Next step was the interaction, so some preparations for the interaction, and then we again commit to the interaction trace that you can see here. Next step would be, of course, in order to do commitment, we also had low degree extension hiding underneath. Composition polynomial is then created. Out of this, we can create the composition oracle, perform out-of-domain sampling, and finally get the out-of-domain sampling composition oracle, which is the virtual oracle I mentioned before, on which we perform the low degree test. If I click into low degree test, you will see the Fry algorithm, which I won't do right now.
Right. Okay, yeah, another file I want to show.
Where it all begins.
Yeah, so so the main function is in a file called CPU prover main. Basically, just invokes eventually the function that Gidi showed. There is one thing that we have here is an object called the CPU statement. This controls the error that we are proving and how we pass the inputs and etc. Yeah, so this is a relatively short function. If I go to CPU statement, let me find it. So one thing that I have here is it's called the CPU trace context. Actually, I want to show you another file. I want to show you the CPU.inl file. And specifically here, there is a nice function called getTrace. This function is responsible for filling the table of values that we mentioned before, the error. And if so, it starts by in this code, it actually fills the things that are relevant for CASM, but later we have we handle the memory of CASM and the built-ins. So we have the Peterson built-in, Renchik built-in, etc. All of them are have as I mentioned. So the built-ins are part of the Cairo L, and therefore we need to fill them. Okay. Yeah. The last thing I want to show is just looking at the directories here. Basically, let's briefly review the stages of the proof. So we start the proof with generating the trace. We saw that. Then we commit. We do an LDE, a low degree extension, and commit to it. So we have in the algebra directory, we have the LDE directory. This is responsible for the low degree extension. We have a directory called commitment scheme. This is responsible for the Merkle tree computation. And we have a directory called channel, which is responsible for the Fiat-Shamir heuristic. The next thing is the out-of-domain sampling protocol, and we should have a directory for this, probably inside the L. Yeah, so for example, the directory of boundary and boundary constraints has to do with the out-of-domain sampling. Later we have Fry, so a directory for Fry, and I think this is basic. This is basically it. We talked about main. Main contains the main file. Statement contains the CPU statement that controls the inputs, as we mentioned. Stark is the entire Stark protocol. I think this covers basically most of the structure of the code. There is the Cairo directory contains parts relevant for Cairo for the trace generation, and I think this is it. Do you want to add something?
Yeah, if you want to understand the prover in a slightly simpler way, we also have an additional error there, which is just for a trace that tracks the Fibonacci series.
Oh.
Not in Cairo, but actually in a very, very simple error.
Yeah,
so that is also available.
Inside the L directory, we have the Fibonacci, and we have Fibonacci correspondingly. We have the Fibonacci statement, Fibonacci. I think we have Fibonacci main, but I'm not sure.
Yeah, it's specifically used for tests. So if you want to run tests on the prover, the unit tests are of course included. But if you want to run tests and you don't want to spend a lot of time on large proofs, and many of these things can actually be tested with very, very simple error, it's typically using the Fibonacci error.
And the grid tree is an example of an error that uses polynomial constraints of the grid tree. Most of our errors, including the CPU error, are of degree 2. So it's an example of an error. Not an interesting one, by the way.
I think we'll open up to questions.
Yes. So time for questions. Yes. Yeah. So the question was about the ability to prove Cairo 1 programs. So the answer is currently we do not have the option to prove Cairo 1 programs. The reason is that the compiler for Cairo 1 does not generate exactly the output that is needed for the Stone prover. This is something technical that will be solved, but currently this is not possible.
It's worth mentioning that the prover actually proves the execution of CASM, And Cairo 1 can be compiled to CASM. So it's just a matter of the toolchain. Once the toolchain is fully implemented for Cairo 1 to the format that the Stone Prover needs, the Stone Prover will be able to, in this current format, in this current release, to prove Cairo 1 programs. It's just a matter of bringing it from Cairo 1 to the CASM.
Yeah.
Right.
So, so you have the code, the compiler from Cairo 1 to Sierra and then to CASM. This exists. There are slight differences between the CASM that is outputted by the Cairo 1 compiler and the CASM that you need for the Stone Prover. Nothing too complicated, but we don't have this logic at the moment.
So you may want to ask yourself, how is it that this prover proves things in Starknet, where in Starknet you write in Cairo 1? And the reason for that is possible is because the Starknet OS program, which is a Cairo 0 program, actually accepts transactions that are written in Cairo 1. So it's also a way to bridge this gap. That's what happens in Starknet. Exactly. So Starknet OS is basically the bridge here that allows you to move that CASM to the format that is needed by the Stone Prover.
Yes. Yes.
Okay. I start again? No.
Maybe start over.
I start again? Okay. All right. So in the proof file generated by the prover, there is a part named public memory. It contains the values that represent the compiled Cairo program. So we can make sure the proof is indeed related to the Cairo program we want to prove. There is also the output of this Cairo program. And in the Fibonacci sequence, we saw that in the output, we duplicated the input in some way, like to prove we are computing the tenth number and the output. And so my question is, if one of the input was a private key, for example, what is inside this public memory in the proof? Do I retrieve that private key if I didn't put it in the output or not?
Okay, so the question is, I'll try to summarize. Let me know if I got it wrong. The question is, what's going to be in this public memory section? Will I find my private key in this section? This was the question?
Yes, if it...
Yeah. Okay, so the things that are going to be in this section are only the things that needs to be there. So you have the program segment. So if you put your private key in the program, it will be there, otherwise it won't. The output segment, again, so you output only the things that you need the verifier to know. So you won't have the private key there. Other memory values are not there. So
AP is not there. The memory segment AP of the core program is not in the public memory.
Can you repeat?
AP, the memory segment AP. In the
so this is the execution segment. This is the name is the execution segment. Let me open the proof file. Public memory, actually, execution segment. So for example, the execution segment, the addresses are 34 up to 95. And if you go and see here, 34 is the last one that is mentioned. Then the next one is 94. So the execution segment is not here.
So we can have privacy with that. What's wrong? Why people are saying it's a validity and not decay?
Okay, good question. Is this prover zero knowledge? The answer is it's not zero knowledge in the mathematical sense, that because it doesn't add randomness in enough places for it to be provably zero knowledge. However, and by the way, this is something that is not very difficult to fix. It's not in this repository, but we have in the past published a zero knowledge prover. So you can merge them in a sense. But in practice, it's practically impossible to generate information from the proof file about the thing being proven, as long as the thing being proven has enough randomness in it. I hope this answers the question.
Yes. Okay.
Okay. Other questions? Okay.
Thank you very much.
Thank you.